I'm Alexandre VERNOTTE. I'm a postdoc at the DISC department of the Femto-ST Institute, and I will be talking about our work as part of the ISITE-BFC SARCoS project. So the project is about defending against false data injection attacks. So an FDIA is when an attacker can inject fake data, so malicious data, into a communication flow, and then it can alter the consensus reached by the node of this network, so making them take wrong decisions because they've been influenced by the false data. The project is focusing on three application domains. So you have air traffic control, vessel traffic control, and intelligent parking systems. The work is conducted jointly with two industrial partners. So we have Smart Testing and Flowbird, both situated in Besançon. So the ADS-B is the latest air traffic surveillance technology. It's a dependent and cooperative technology, which means ground stations depend on aircraft to send their surveillance information, so like position, altitude, etc. In turn, aircraft depends on GPS to obtain their position. The goal of ADS-B is to obviously reduce the surveillance cost and improve the position accuracy of the aircraft. The very end goal is to reduce the size of the airways and, make more aircraft fly at the same time. So this is an example of ADS-B messages as received by capable sensors. So you have a sequence of information. So you have the message type, you have the ICAO, which is the identification number of the flight, the emission date, and then some surveillance information, such as the altitude, the position, ground speed, etc. Well, the problem with the ADS-B is that it was not designed with security in mind, which means all the information is sent as clear text over the air. There is no encryption, no authentication, which means that anyone can listen to the traffic. This is why you have websites such as Flight Radar 24. But if you have a bit more equipment, you can also get close to an antenna and block all messages. And then you can also inject false data and also alter the genuine incoming data. So that's why this is false data injection attacks. Well, it's not as risky as it is because there are many surveillance technologies working jointly, but this is a risk that needs to be handled. So in SARCoS, we propose a testing framework. We want to simulate false data injections attacks only using the data. So what we do is that we first collect a sequence of genuine ADS-B messages, so using an antenna, for example. We put it in our tool, and then we apply an FDIA scenario that we have designed before. So in this example, we change the status of the flight from 4022, which is transit, to 7700, which means full-on emergency. There's a big problem. So our tool then automatically modifies the messages that we have asked it to do. And then we can replay the obtained altered recording to the surveillance system that we are trying to test against false data injections, with respect to the temporality of the messages, of course. And so this way, we can simulate that an attacker has tampered with the surveillance data flow. So we have 4 steps: acquisition, FDIA scenario design, then we have the automated alteration, and then we execute the altered version of the recording. So to get genuine data, we have 2 different ways. So first, we can use our antenna. So this is a picture of my office. But of course, we need more eclectic data to have more meaningful test cases. So we can also get our data from the OpenSky network. It's a community-based ADSB message database made by academia for academia. So it's a very good opportunity for us. We can get a lot of data. You have many, many people with antenna connected all over the world that send their data to the OpenSky network. And then we ask the ATC expert to, well, explain, to define what is an FDIA scenario. So we propose a textual domain-specific language to design FDIA scenarios. It includes, well, some ATC-specific terminology. So in this very simple example, we ask our tool to change the identification, ground speed, and call sign values of some specific flights during a determined time window, so 40 to 50 seconds from the beginning of the genuine recording that we feed it. Of course, this is a very simple example. We have more interesting examples. So in this case, we can simply specify waypoints, and our tool will automatically change the messages to create a trajectory that looks real and makes the aircraft pass by the waypoint that were specified. So our tool is capable of interpreting these scenarios and automatically using, well, specific algorithm under the hood to directly modify the ADSB messages to obtain an altered version of the recording that still looks real. And then we can directly execute the altered version of the recording to the surveillance systems and then, well, evaluate its resilience against FDIA. So did it accept the data or did it not? Did it refuse it? So in this example, it's an aircraft splitting attack. So we make the aircraft going in all kind of directions. So we multiply all the messages. And so if the surveillance system was to accept this data, this is what the air traffic controller would see. So it could be kind of a problem for him or for her. Now we're working on testing surveillance systems. Now we want to also detect FDIAs using machine learning. We want to use our testing framework to generate data sets that will contain, well, synthetic but realistic false data injection attacks. Using this tool, we could train and test supervised machine learning architectures and also test unsupervised machine learning architectures. But it needs some evolutions. So first, if we want to do supervised learning, we need to label all the messages, genuine or altered, if we have changed one of its values. We need massification capabilities, so that using one scenario, using like list of values, we should be able to generate a complete data set of thousands of altered version of one recording, and also reusability capabilities, so that we can apply an FDIA scenario to several recordings without being stuck with some information of one recording. So regardless of the method, this is a time series problem. For supervised learning, we want to classify the sequence of n messages, so genuine or altered. For unsupervised learning, we will calculate an anomaly score for each sequence, and if it exceeds the threshold that we have decided, then we deem the sequence as anomalous. We have very early experimental results with supervised learning. So we're trying to detect a progressive altitude drift, and we have some encouraging results. For unsupervised learning, we want to, well, make it, we split it a little bit so that we would have a model specified for each phase of the flight, so a model for ascending, cruising, and descending. And finally, we are doing a joint work with the temps fréquence department of the Femto Institute. This time, we want to stop simulation and do the real thing. So we want to actually inject false data, not in the real communication of the air traffic control, but in a controlled environment, of course. I have to say the picture is not our setup, but this is something we are striving for. The goal would be to bridge the gap between the scenarios that I've showed you before and, well, low-level attacks that would be performed thanks to the temps fréquence department. And maybe we would have, in the end, a testing framework that is both for software, the surveillance system, and also a physical testing framework for the the physical devices. Thank you very much for your attention.
So I think that most of you are afraid about this talk, and in some way I'm quite happy to not take flight during the next month. So is there any question you have before your next flight? I just have a basic question. So I understand that if the trajectory is not accessible physically, so if the attack provides something which cannot be provided physically, you can identify the failure. Mm-hmm. But now you take the example of one attack at the beginning that is just to switch to emergency, so to have an emergency flag. Mm-hmm. But in fact, how to know that it's a false emergency flag? So what's the difference between a real emergency situation and an emergency flag coming from an attack? It's not clear how you can classify.
Yeah, well, I don't think you can make the difference so that either you would have to go low level and say that the message, because of its technical characteristics, so for example, the angle of emission or the power of emission is not, doesn't correspond with something coming from an aircraft. This way you would make the difference, but well, you need to have this defense in place. If you don't have that, then it's a message like any other, and then the controller has to talk with using voice to the pilot to make sure that there is no problem.